context of applying cultivation. Then talk about how we find illustrate the important here of large dams. Bank, those of clarified the bank dam, very large reservoir, large. That water is down drain. The big risk of this type of structure at sea might erode away some of the shell of the dam or in. That's exactly what happened to the dam in the 90s. Luckily, they noticed rest of the dam the other dams here, depths want to avoid type near miss or lapse. We're also in very well aware of the risk of sorry. But we're not just interested in preventing disasters, we're also interested in driving forward our economies. For example, a key issue is reducing the cost of the foundations of offshore wind turbines. The foundation cost can take up a significant proportion of the overall cost of turbines. If we can reduce the price per kilowatt hour of energy produced in this manner, then low carbon energy becomes much more viable, and that has benefits, as we know. So in geotechnical engineering, traditionally, a lot of effort has been expended in laboratory tests. For example, this is the Soil Mechanics Laboratory at Imperial, and this has given us a lot of information about how soil behaves. And through these experimental work, we know that soil is a very complicated material. It's non-linear, both its strength and its stiffness are strength dependent, and it exhibits highly complex material behaviors such as non-coaxiality. But DEM is well suited to simulate sand. When we're talking about sand, I'm talking about a granular material where the grains are sufficiently large that the surface interaction forces don't have a significant influence on its overall behavior. We can take a cube of sand and idealize it with a DEM model. And if we do this, we can see that DEM capture all of these features of sand response that have been well established in the experimental soil mechanics. And we're very well aware in this room that DEM and particle-based methods are very powerful. We can do a plot of the number of published papers involving particle methods, and we can see that there's an exponential growth. These data just come from Web of Science, not focusing on any particular discipline. But if we look at geomechanics or geotechnical engineering, we can see that there is also a significant increase in the amount of research that's being published using DEM. And this is just an index of activity using DEM. So in geotechnical engineering, we can see cases where DEM has been used to look at boundary value problems, such as the work they've done here in Barcelona on cone penetration testing, or it can be used in a more fundamental way to complement the knowledge we've built up through experimental research, try to explain why soil behaves how it does. But I think what we need to be very aware of throughout our attempts to EM and geotechnical engineering is that sand is a natural material. This is a revised geological cross-section illustrating the geology of London that was developed as part of the Crossrail project over the past 10 years. And I'm showing that to indicate that engineering practice is very conscious of the geological setting of the materials it works with and the importance of that as indicated through the development of this geological data. And because sand is a natural material originating out of one of the geological strata, it's a very complex material. We have complex morphologies, we have complex surface textures, and also complex patterns. And we know that the fabric, or the way the particles pack around each other, is important. These are data from Joana Fonseca's PhD. The green line show a reconstituted sample of sand. The red lines show a sample that is intact, and we can see that the material behaviors. For this sand, we could go out to the field and sample the fabric as it is in situ. That's rare. We can only do this because it's a locked sand with a particular fabric that's somewhat like a jigsaw, so the particles stay together if you carefully cut the blocks out. Another problem, challenge posed to us is just the extent of the project. We saw this with the dams, but we also see this with development turbines or compaction of large straits of sand to enable construction. So then how do we achieve impact when we're looking at this natural material and when the project is such a large scale? And in some cases, we can clearly see how we can use DEM research to directly influence geotechnical practice. In other cases, it seems that the benefit is more to use DEM to inform either continuum modeling or to use it to develop experimental soil mechanics research and have an indirect practice. So I'm going to just propose that there are 3 ways that DEM can effectively impact practice. And the first, provide a solid theoretical basis for some of the correlations that are used in geotechnical engineering practice and data interpretation. DEM can also be used to inform the development of instrumentation in the lab or in situ. And it can also supplement experimental studies to enable us to develop better, more robust, more reliable. And I'm going to give just some examples on these headings to hopefully provoke some discussion. And I'm going to firstly think about the state of our material, talk a bit about seepage in terms of our fundamental basis for correlations. I'll then refer to some of the work we've done on stiffness, and finally talk a bit. So in soil mechanics, when you take your first soil mechanics lecture, probably on the first day, you see a diagram such as this from Craig's Soil Mechanics of an assembly of particles that are touching with some void space around them. And the fundamental idea is that the particles are transmitting stress and there's some space around these particles. And we quantify our package density using a void. I know that's somewhat different from the definitions of package density used in other disciplines, so I'm just putting it up here for clarity. And we also talk about the bulk density of the material. And these measures of density are very important. For example, when we're interpreting geophysics tests in the laboratory to estimate stiffness, we relate our stiffness to our shear wave velocity using the bulk density. And then when we're trying to predict how our stiffness will vary with package density and stress level, we have what we call a void ratio correction function that describes how density is stiffness. And some work we've done has looked at how our measure of stiffness obtained using dynamic methods relates to measures of stiffness obtained using static probes, or just the slope of our stress-strain response. And these are data from some DM simulations carried out on an almost monodisperse assembly of spheres. And we can see when our sample is dense, we get good agreement, and when it's loose, the agreement is good. And we're trying to understand this by interrogating DM data. But that led us to think a bit about what do we mean by void ratio and density. And if we are to really look at what is the density of the active grains that are transmitting stress in a material, we can look at a mechanical void ratio that considers the grains that don't transmit stress to be part of the void space, or a mechanical bulk density, which is a similar definition. And to assess how similar this might be to the actual void ratio of the material that's used in geotechnical engineering practice, we did a simple parametric study where we created a number of different samples with a linear, continuous particle size distribution and compressed these isotropic 500 kPa using periodic boundaries. And what we see then is that quite a large portion of the particles, even when we have an almost uniform pattern, are inactive. As our coefficient of uniformity increases and our polydispersity increases, so too does the proportion of inactive particles. These inactive grains tend to be small, so when we look at the volumetric proportion, it's significantly smaller than the proportion by number. But if we look at the influence of this on our measures of void ratio, we can see that the mechanical void ratio is consistently larger than our conventional definition of void ratio, and for loose patterns, this difference is quite big. I should have clarified that we controlled our pattern density using the coefficient of friction of our particles. Similarly, if we look at bulk density, we can see that there is a difference. It's not as big as our difference in void ratio, but it is finite. So these errors and the density dependency of the difference between the pattern density we measure in conventional experimental work and the density of the real stress transmitting particles, that leads us to question some of these fundamental measures of density that are used in geomechanics. And we've known there are errors with these for a long time when people think about gap-braided materials. But what we're seeing is this is a more general problem, not just restricted to particular particle size. Seepage is obviously a significant issue. I've already mentioned the problems at Bennett Dam. But filters and filter design is an issue for engineered levees, dikes, or flood embankments, as well as for embanked dams. And the design of filters has been addressed in a number of recently developed guides for practice years. And filters are a key element of their flood embankments or embanked dams. Filters are granular materials, and their role is to keep the base soil, which is a low permeability material, in place. If a filter is ineffective, we'll start to see migration of this fine, low permeability base soil, which we call when we're looking at filter design, that could form, for example, the core of an embankment dam. And what we want to prevent is backward erosion of this finer grained material, which could cause significant problems with your dam or your flood bank. And traditionally, geotechnical engineers use Terzaghis filter rule, and this filter rule compares the D15 of the filter to the D85 of the base. 15% of the filter particles are smaller than 50% of the filter, 85% of the base particles are smaller than 5%. And during Tom Shire's PhD, and Tom is here today, he created a number of model filters, again using DM, and again having linear gradings and using this measure of polydispersity that's used in practice. And what we were able to do when the DEM model was created is to use a Delaunay triangulation-based approach to partition the void space and identify the constrictions in the void space. And the constrictions are the narrow points in the pore space, and these are where we understand the base particles will be trapped. And we verified that this way of partitioning the void space made sense from a fluid mechanics perspective by simulating, for some cases, the flow in the void space. And so just as we can have a distribution of particle sizes for our filter, we can also have a distribution of the constriction sizes. And in this case, we look not at a volumetric distribution, but at the distribution of constrictions by number. And we can see that until we get to a coefficient of uniformity of 3, our constriction sizes are becoming bigger. However, if we normalize our distribution of constriction sizes by 15, as Terzaghi suggested, we start to have a narrow range of filter sizes. And that indicates that Terzaghi's idea that the D15 of a filter tells you something about the constriction sizes is indeed, there is indeed a basis for it. But moving on from there, we've looked at how we can simulate the migration of the particles through the filter itself. And we discounted the idea of using fully resolved CFDM because of the computational cost and the necessity to accurately get information about flow in the void space. And instead, we used a network-based approach where we took our partitioned void space and used these voids nodes in a network model and the constrictions to give information about edges in that model. We then solved for the fluid flow on that network and used the information about the fluid flow to simulate the migration of the filter particles through this network. So the likelihood the filter particles are introduced into the network and their migration through the network is simulated by taking information about the flow rate out of each particular void. The model can simulate clogging of constrictions, and also it captured the case where an individual void might fill up with its finer base materials. And using this network model, we can then look at some of the empirical guidelines, again, that are targeted at practicing engineers. This is a characterization developed by Foster and Fell about 20 years ago, and this is a tool to enable engineers to look at the filter performance in existing structures and to assess what the risk might be there by saying, well, a filter provides a seal with no erosion, with some erosion, or a case where there could be continuous erosion. And we used our filter model to look at the boundary these cases. So simulating the amount of material that gets, or quantifying the amount of material that gets through our model of the filter, and then looking at these empirical guidelines that have been proposed in the literature, going back to Terzaghi, but also looking at more recent guidelines. And our simulation provides a very controlled way to assess the efficacy of the guidelines, looking at these different criteria. So the second thing I wanted to talk about was using DEM to form the development of instrumentation and thinking about soil stiffness. So these are some data on planet sand. It's the sand that exists under London, and high-rise buildings in London often have foundations going down into the sand. And obviously, if we want to predict the behavior of these structures, we need to understand how the stiffness of the sand varies with pressure. Traditionally, over the past 20 to 30 years, a tool that's become very popular for assessing stiffness in soil mechanics testing are bender elements. And these are piezo-ceramic elements that are inserted into the soil sample. So you can insert two sets of elements at opposite sides of the sample, and using them generate a small amplitude wave or a stress wave, and you can monitor how fast that stress wave moves through the material to get your elastic wave propagation speeds. And we collaborated with the University of Bristol to do some DEM simulations of tests on samples of Ballottini where they measured the stiffness using Bender elements. In our simulations, we modeled our Bender elements as point sources. And here are some data from that collaboration. The top line indicates data from the experimental work at Bristol. The bottom line indicates data from our DEM simulations. And you can see that we're getting quite good agreement the lab test, the DEM simulations. And that gave us confidence then to use our DEM data to look in a lot of detail at what's going on when you put in such a small point source into the sample. And we can see that the energy that goes into the sample due to the movement of a particle depends on the packing around the particle. The local fabric of the material around your point source is going to affect how much energy gets into the sample. That's going to affect your signal-noise ratio and ultimately influence the accuracy with which you measure your stiffness in the material. So realizing this issue with using a point source, especially when you have coarse sand, started to work with during Masahide Otsubo's PhD on an alternative way of generating stress waves in a geotechnical lab, and that is using planar piezoceramic elements. So again, these can introduce a small disturbance into the soil, but they act over a larger area. And we looked at different configurations of shear plates to understand how this technology could be used and what were the limitations of its use. In the bar test, we again used Ballottini, and that enabled us to run parallel DEM simulations, also look at this technology. And here are some data from the DEM simulations. We had excited different areas of the base, of the top of the sample to generate a signal and monitored it along the base. And here we see the results of our stress measured at our receiver and our DEM data. And what we can see is that when we look at just a stress coming from just a portion of our boundary, we can clearly see that the signal we receive and monitor is corrupted by a wave. We see this near field effect that's well known in experimental soil mechanics. However, if we add the signals together so that the entire surface is excited and the entire surface is used as a receiver, this near field effect becomes absent. Similarly, in the lab, we can excite just part of our top plate or our bottom plate, and the same with our receiver, and receive only over part of the surface. Again, we see this wave contamination, but in the lab, we still see this even when we add our data sets together. And we can look at how the signal quality varies with the area of the transmitter and the area of the receiver plates in both the experiments and our DEM simulations. And we see that the amplitude of our received signal depends on both the area of the transmitter and the receiver. This implication for signal quality has a knock-on effect into the interpreted data in terms of the shear wave velocity that we calculate the approach that is commonly used in experimental soil mechanics. So the third aspect of material behavior I'd like to talk about is strength, and we can all understand why soil strength is important. What you may not be aware of is that in soil mechanics, a lot of emphasis on the critical state line. This is the void ratio that samples will attain during shearing, and this void ratio will depend upon average or the mean effective stress. And this is taken as a reference state in soil mechanics. And we can measure how far we are away from this reference state by looking at the difference in void ratio between where a soil is at any given point from this critical state line by looking at by projecting that point up onto the critical state line at the same stress. And working in the 1980s, Jeffries and Bean showed that there's a clear correlation between your peak angle of shearing resistance, or your shear strength of sand, and your initial state parameter. If you have a negative value, that means you've got a very dense material, stronger. Positive value is a loose material. Which is the problem with Jeffries and Bean's data is they were developed for axial testing, axisymmetric stress. In the field, even under the center of a perfect round foundation, your stress state is not triaxial or axisymmetric. Here we see contours of B, which is the difference between your intermediate and minor principal stress divided by the difference between your major and minor principal stress. And even in this case, we might anticipate the axisymmetric. It clearly isn't. And we test for different p-values using either the cubical cell or the hollow cylinder apparatus. But the problem is these experimental tools, while they're very, very good, they're not reliable when we get to large strains. So we can't reliably get our reference state under a general stress experimentally. We can, however, do this with GM, which is what we did, again using a cubical sample, periodic boundaries, where we can deform our sample to large strain. And when we do this and we plot our peak angle of shearing resistance against our initial state parameter, our data lie below Jeffries and Bean's database. And that's not surprising, because in this case, we ran GM simulations for years. However, if we look at all of the correlations that Jeffries and Bean together, we can actually see that our model is quite a good agreement. For example, if we look at the difference between our peak and critical state strengths, and we compare this with our initial. We can then use our model, recognizing that it look at this critical state framework general stress state to interrogate some of the models that are used in practice that have developed using a triaxial data obtained from triaxial stress state, and look at their performance under a general. So I think these are ways we can use GM that can be incredibly useful to current engineering practice. Moving forward, I think there are challenges with regard to the number of spheres in our simulations, or the number of particles in geomechanics, how we handle particle ecology, coupled simulations, and I'll talk about this. So this is a set of data that I've putting together over the past decade or more on the size of particles of simulations in EM studies published in geomechanics. And they're actually very small. Rarely do you see simulations, journal publications that exceed about 100,000 particles. I think there are cultural reasons for this. A lot of work that's carried out in soil mechanics and geotechnical engineering uses commercial codes that work in Windows environment. But I think this limitation on the number of particle sizes has implications for the quality of work. And we did quite a simple study where we looked at different sample sizes, simulated them using the commercial code PFC with rigid wall boundaries, compared that to simulations with periodic boundaries using lamps. And what we found was there was quite a significant sensitivity of the material response to sample size. The sample with periodic boundaries contracted, and it was much less stiff than these rigid wall samples, all dilated. And we could resolve this by looking in detail at what was happening at the center of the material and realizing that there's quite a large region close to these rigid walls at the lower pattern. There's quite a significant boundary. But we see this sample size effect even if periodic boundaries when we go to samples that have quite a difference in particle size in their composition. And here are some data that were recently generated by Adnan Sufyan when he was working at college and looking at triaxial test simulations of gap-rated materials and showing a clear sample size effect for this material, particularly. So we need to be mindful of this when we're doing our simulations. I've already showed you these images of particle morphology. Additionally, we assess morphology using a visual like this chart by Crumline and Sloss. And in recent work, what we've been doing is trying to come up with ways to effectively capture the shapes in a DM simulation by taking images of these particles, looking at their distance map, and using the distance map data to develop them. So this is some of the work we're doing 2D to develop. Thinking about particle fluid interaction, I've already explained how important that is, both from the perspective of bank dams, but also and the risk posed by that. As you're probably aware, all of there's approaches we can use for PDM. We can use a force resolved, force approach, where we don't fully resolve the fluid flow in the void space, and we use some kind of fluid particle interaction force, and average our void ratio over a cell that's larger than particles, or we can fully resolve the flow. In geomechanics, simulations with fully resolved flow are very rare. To get a sample that's representative of the soil are. So in order to kind of advance work in this area, what we've done in collaboration with Bern van Wacht is look at the empirical drag expressions that are used in geomechanics DMCFT expressions and assess their efficacy by simulating flow through packed beds of spheres at packed densities that are relevant to soil mechanics. And what we can see is that the expressions that are used in the unresolved flow simulations do not give a good match to the drag on the particles across the full range of particle sizes in our sample. They underpredict the drag on the large particles and overpredict the drag on the small grains. And this is an issue when we're thinking about erosion and when we're really trying to understand. And the final thing, we have started to develop ways to mitigate this, either using the local porosity or again going back to our flow network approach. And both of these areas seem to show promise, so we're going. The final thing I want to talk about is clay, because arguably clay poses more problems to geotechnics. We'll talk about the dominating influence of clay phase. 5% clay in your sample and you're getting a different material. And the challenge is twofold. We have a very complex particle, but we also need to think about the charge, the surface interactions. This is a schematic diagram of kaolinite, active clay. And what we can see here is that the charge or the interactions between particle surfaces are very dependent, and our interactions are either positive or negative, meaning we can have either repulsion or attraction in our grains. This affects the mechanical behavior, and you can see here the tendency of behavior just simple odometer test. Additionally, in our textbooks, we explain this chemical behavior using the DLVO model. That was developed in the 1950s, generally accepted in soil mechanics. If we look in more detail at that theory, it has some limitations. Some of the assumptions in it pose significant limitations to its accuracy when we look at active clays. And it also requires a knowledge of surface charge or surface potential. We simply don't factor that. So what's clear to me is we need to go beyond our current state of empirical we're looking at clay, more atomistic or subparticle simulations to better understand. In the work we have done, where we've simulated kaolinite using the Gay-Byrne potential, which is a generalization of the Leonard-Jones potential for ellipsoidal particles, we can see there is significant rate dependency. It's difficult to capture the fact that our interactions simultaneously repulsive and attractive, depending on the orientation. Contact detection is tricky to reduce the cost of it, and it's hard to find what is a reference. And what's also becoming clear as I look into the literature is that if we're going to start to look at active phase using this type of tool, they have very complex problems. And while an ellipsoid might be a valid idealization of kaolinite particles, when we look at smectite or event, we're going to develop. So hopefully I've given some idea for those of you who are not years of our motivation challenges associated with tech. I've put forward some ideas about how we can use EM now to have practice, and also laid out some of the challenges that I see that inhibit our ability to have more of an impact. And finally, to acknowledge all the current and former PhD work I've